Hey everyone, I've been getting some questions about the quantum numbers and how we decide which ones are good and which ones are bad and what the ranges for each are. So I just wanted to use this figure here to walk through that a little bit for those of you who might not be as familiar. So we've got a few different quantum numbers. The first one, the one that we talk about the most, is called the principal quantum number, and it's given the symbol n. So the principal quantum number, in this diagram that I've got, is really just that first number that we see for all of these different orbital types. So we've got 1, 2, 3, and a few different spots here, and then 4. So those were the quantum numbers we had. Even with the hydrogen atom, we had all those different levels, and they go up in terms of integers, and that's called the principal quantum number. And so that hasn't changed, and the values that we can have n take on are really anything from the first one, which is 1, all the way up to conceivably infinity. It could be anything, but they're integers. So 1, 2, 3, 4, 5, on and on and on and on and up. Now, the next quantum number, the one that we use to distinguish between the different types. So you'll remember we started getting what was just one energy state. It started to split, and so we'd get these set of 2p orbitals or set of 2p states, and then we'd have a 2s state. And that was fine, but then in the principal quantum number 3, we had more than that, and we'd have more than that still in the fourth if it was on this diagram. So how do we make sense of that? Well, the other principal quantum number that we use is called the angular momentum quantum number. It's given the lowercase l symbol. And I've brought back a table that I talked about a little bit in class up here in the top right-hand corner here. L has various numerical values that it could be, and each one of those numerical values comes with an associated symbol, which is really just a letter. And so in this diagram over here, the common names that we associate to all of these different energy states are labeled according to the letter of their angular momentum quantum number. So my angular momentum quantum number could be 0, in which case the corresponding letter is S, and I see I have some examples here: 1s, 2s, 3s, 4s, on and up. And some other examples are 1, for example. So if my angular momentum quantum number is 1, it's a state that I would call P. And so here's an example there, the 2P states. So how do I figure out what values of L are available for a particular principal quantum number? If you look at this diagram, you might be able to detect a pattern, and that is that when the principal quantum number is 1, there's really only one state available. When the principal quantum number is 2, there are 2 states available. When the principal quantum number is 3, there's 3 states available. And in 4, there's 4 states available, although they're not on the diagram. The point is that pattern seems pretty evident, and it will always work for you. So there are as many choices for L as there is whatever your principal quantum number is. So if your principal quantum number is 3, then that means you have 3 different choices for L. So what are those choices? Well, the choices for L always start at 0. So you'll notice there's always an S state for every principal quantum number. And then they go up from that depending on how many available angular momentum quantum numbers you can have. So for example, if we were at the principal quantum number of 3, we know that we have 3 L's available. We also know that L has to start at 0, so I would have 0 as an option. I would have 1, which is P states, as an option, and I would have 2, which are D states, as an option. And a way that we summarize that, more or less briefly, is we say that L can take on any value from 0 all the way up to n minus 1. Okay, so just to highlight that point, if you have a look at, say, our 2's, so we know that for a principal quantum number of 2, we can have 2 different states, or 2 different angular momenta. And so we'll start with the first one, which is 0, and we have a 2s state, and we'll go up to the second one, which is 1, and that's a 2p state. So notice if we went to 2 states, we finished at the number that was exactly 1 less than the principal quantum number. And so that's a coincidence that will work forever. So as you go all the way up this table and all the way up really through the periodic table, what you'll find is that works every time. And so the available set of L's, so the available set of angular momentum quantum numbers that you have correspond to every number from 0 up to the principal quantum number you have minus 1. So that's how that works. Now the other quantum numbers that we've got, the other one that we talked about in class is m sub L. So this is called the magnetic quantum number. And the magnetic quantum number really just is a number that helps us keep track of how many degenerate states. So the word degenerate means of equal energy in this case. So if I look at, for example, my 2p states, I notice that there are 3 of them available. So there are 3 available 2p states. I have labels for each of them, although because of the fact that they're degenerate, it really doesn't matter which one you assign which label. And it basically goes as follows. If you take all of these sets of orbitals, so the 2p, the 3p, the 3d, the 4p, whatever, if you put a 0 in the middle of them, this is, you don't have to do this, but if you put a 0 in the middle of every single one, and then you count in integer steps on the right and left, you'll see that you have 1 in all this case, and 2 in that case, and 1 there. And then if you go in the negative direction on the other side, you have minus 1, minus 1, minus 2, minus 1, and minus 1. So what happens is here I'm labeling all of these different degenerate states, starting with 0 in the middle, and I see how many there are available. So in the case of the p states, I've got 3 available, and they are labeled starting at 0 and going 1 in either direction. And so how do I keep track of that down here the way I've kept track of my other quantum numbers? We say that the magnetic quantum number runs all the way from negative L to positive L. So it runs through that set of values, including 0. So if we take our 2p example again, p is my angular momentum symbol, so that's a quantum number of 1. And so my magnetic quantum number values can be anything from negative that all the way up to positive that, which in this case is 1. And so that's what I've got. And this works equally well for any other set, like, for example, the 3D sets. So if my angular momentum quantum number is associated with the letter D, which means that L is equal to 2, according to the table over here, then my available values for my magnetic quantum number run all the way from minus that number, which is 2, through 0, to positive that number, which is positive 2. So however you look at it, the range of my magnetic quantum numbers run from minus L to plus L. Now the final one, which we actually didn't spend much time on in class, is the spin quantum number, which is given the symbol m as well, but this time with a subscript s. That really only ever has 2 values, minus 1/2 or plus 1/2. You'll remember our discussions about the fact that electrons come in 2 different spin types. So in any one of these states, be it the 4s or one of the 3d states or one of the 2p states, it really doesn't matter. We've talked about the fact that we can put only 2 electrons, a maximum of 2 electrons in any one of these orbitals, or in other words, allow 2 electrons to be described by any one of these orbitals. And so one of those electrons will have to be one that has a spin quantum number of minus 1/2. The other will have to be a spin quantum number of positive 1/2. So those are the only available numbers for your spin quantum number at all the time. And so this really defines the full set of 4 quantum numbers, which can define really any electron in any part of this diagram or any other diagram that's bigger than this one and includes more orbitals. It's a totally general set of rules here. And that'll allow you to determine if a particular set of quantum numbers that somebody proposes to you is valid or not, which is one of your sapling assignments this week. So thanks for the question, and keep them coming.